this video, we're going to look at a related rates problem involving a right triangle. And we'll have some sides moving and some sides staying the same. So as we read this, it says an observer stands 200 feet from the launch site of a hot air balloon. It rises at a constant 10 feet per second. How fast is the distance between the observer and the balloon changing 15 seconds after launch? Okay, so the first thing we want to do is draw a picture, and I definitely don't have a lot of artistic talent, so I'm just going to draw my person, and they are 200 feet away, and then it doesn't matter what I do when I draw this hot air balloon. To me, it just looks like a light bulb, so welcome to my light bulb. All right, so there's the hot air balloon, or light bulb. All right, so what's going to happen is that the balloon starts off on the ground. It's going to rise. It's going to rise at a rate of 10 feet per second. And this person is not going to be moving, and we're assuming that this balloon is just going to rise straight up. Okay, so what I want to know is, what's the rate at which this side is changing? Okay, now, yes, they stop time and they're talking about 15 seconds after launch. But what happens to a lot of students is they put a lot of numbers in right now. Okay? We don't want to start solving for this triangle at 15 seconds yet. What we want to think about is what's changing in the picture. And what's changing is that this balloon is rising up. So we'll call that Y. And this distance x is changing. So as the balloon is rising, this side's changing, this side's changing. This one is staying fixed because they're assuming the person's not moving and this is going straight up. All right, so if I was to ask you what equation does this look like, hopefully you'd say, oh yeah, Pythagorean theorem. So 200 squared plus y squared equals x squared. Okay, yes, we are going to get to that 15 seconds in just a minute, but for right now, we want to look at what's going on in general in this problem. Okay, now, to introduce time in this section, we're going to take the derivative with respect to time. Now, some students are tempted to do a power rule on this, but this is, 40,000, I believe. The derivative of this is 0. Okay? The derivative of y will be 2y dy dt. And the derivative of x squared will be 2x dx dt. Okay, now what's going on here is that this is my side y. Dy dt is how fast it's changing, and we already know that. It's 10 feet per second, so that's dy dt. X is the hypotenuse of our triangle, and dx dt, this is actually what I'm going to be solving for. This is what I want to know as my final answer of the whole problem. All right. Now is when we want to talk about what happens at 15 seconds. So after 15 seconds, what's going on here is that this 200 is still here, but this side would be 15 times 10, because if I'm rising at a rate of 10 feet per second, then this would be 15 seconds times 10. So y is going to be 150. All right, what about x? Well, to do this, I would just use the Pythagorean theorem. So this side will be the square root of 200 squared plus 150 squared. And I'm just going to go ahead and do that as a decimal. And we end up, oh, it's a perfect 3, 4, 5 triangle. Okay, it's 250. Okay, now we're going to plug in all those numbers down here. So what that's going to do is I'm going to get 2 times 150 times 10, 2 times 250, and then here's my rate that I'm solving for, dx dt. So if I go ahead and divide by 5, this is 500, if I divide by 500, what I'm going to get is that this is going to end up equaling 6. All right, so to finish off our problem, we want to put units on our answer, and we want to kind of write a sentence. So the units here are, this is the rate at which the side is changing would be 6 feet per second. Okay, so the distance between the observer and the balloon is changing at a rate of 6 feet per second. Boom. All right, good luck. You may have to watch this one again. Make sure as you're setting up problems that you're paying attention to what's changing the whole problem and what's staying fixed the whole problem. Good luck.